Welcome. Today we're going to talk about the divergence theorem. So the divergence theorem is another one of our vector calculus theorems, and we need to put it into context. So what I'm going to do is first present Stokes' theorem. So recall that Stokes' theorem is a way of computing a work integral where we have some closed path embedded in 3 dimensions. It's a closed loop. It's a simple loop. And that is equal to the integration over some surface that's embedded in 3D that has a boundary. So here we have our C, and we have some sort of surface that's attached to it, like that. And it's the work integral done over that boundary. If we have some outward direction, we'll call our normals, is equal to the curl vector field dotted with the normal of our surface times the little patch of surface. And we add all those up to get the work integral we do on that boundary right around there. Okay. So what this is a great example of is something that's 2D, a calculation of a 2D surface integral that helps us understand or compute the work involved on a 1D loop. Okay, so we see that relationship between 2D objects and 1D objects. So one would wonder then, is there another sort of theorem that involves 2D surfaces going back and forth with a 3D volume integral? And that is precisely an expression. The divergence theorem is an example of such an expression. So let's write down what the divergence theorem is. It's going to be, and so Stokes' theorem and of course Green's theorem, the analogs, were always dealing with work integrals. But now what we're going to go back to and talk about with regards to surface integrals is flux integrals. So we want to find the flux. So we'll talk about the flux through a surface, which we'll call S. And that's going to be equal to the double integral over our surface of our vector field dotted with an outward normal, ds. And what we're going to find out, and this is the expression of the divergence theorem, is that it's equal to the volume integral over the solid volume inside of the surface of the divergence of our vector field dv. Okay. So there's our flux through the surface S. So that is called the divergence theorem. Okay, so how do we understand it? So again, as always, we want to know why. So recall that the divergence, we stated without really proving it that it represented, or it gave us some measure, a measure of the expansion or the contraction of f at h point x, y, z. So what do we mean by this? Is we have some point x in three-dimensional space, and if we have at every point we have a net expansion of our vector field, this means that divergence of f is greater than 0. And if we had something like this, sorry, no, I'm making a mistake here. This would mean that there's an oh no, I'm right. Yeah, so that would mean that there's an expansion, and here would be a divergence of our vector field less than 0, which means that things are contracting in on that space. And so, and then another example would be if you have a net balance. So you have some coming in, some coming out, and that would indicate a divergence equal to 0. Okay. So if those are the properties of the divergence, but we haven't really explained why this is true. This was just a statement that we made. But it turns out the divergence theorem is precisely the expression of this aspect here. So let's talk about why. So let's actually give a proof. Now we don't always give proofs to our theorems, but we'll give a proof for cubes. A cube region, or I should say a cube region. So we'll say that E is the set of x, y, z, such that x is between A and B, y is between C and D, and that z is between E and F. So again, this is simple enough to write. Here's our cubic region. So we have A and B, C and D, and then E and F. Okay. So the proof here is really a direct computation. It just explains exactly what we're talking about. So here's some region, and what we want to do is compute the flux. So we want to compute the flux. So the goal here is to compute the total flux through the cube. Okay, so what we need to do then is actually account for all of our normals on our surface, right? So we have 6 of them. We could write them down as such. We can write them down as, so these are all our normals. So I'm going to call that the normal AB, and this will be the normal BA, right? Because this is going from A to B, and it really is in that direction. Likewise, that would be the one coming out the back would be the normal CD, and this would be the normal DC, right? And likewise, that's going to be normal FE, and this will be normal EF. All right, so there's 6 of them total. So we know that the flux is the flux of over our surface, and our surface is just every side of this box, for some vector field. So we have to write down F is equal to P, Q, and R, our usual convention, dotted with our normal ds. Okay, and that's going to be the equal of the sum over all 6 sides. And we'll just call those SI, F dot N, and I'll just call those NI for now, and we can write them with our subscripts over there later, DS. Okay, so that's the total flux, and it'll be the sum over all 6 sides, and we just have to compute all 6 sides of those. So what we'll do is we'll just talk about this side and that side first, and see if we can intuit what the other sides are going to be. So again, NAB, that vector is clearly 1, 0, 0, right? It's just pointing straight out that way. Likewise, NBA is going to be equal to negative 1, 0, 0, right? All right, so if we take these 2 sides, and I'm going to say so I'll call this the X flux. So that's just the flux coming out of coming through there and coming through these two sides, just this side here and the other side right here. All right, so that should be then, and so that should be, remember our F is going to be P, Q, and R, because we don't really care about anything else though except for P, because that's the only vector, that's the only component of the vector that's going to matter for this. So what we really get is that, sorry, this needs to be a double integral there. We're going to get a double integral over our surface, which is going to just be P. We'll do the NAB integral first, and that's going to be over this whole square here, which I'll indicate it as the surface then is going to be CD cross with EF, those two intervals. That's what creates this box here. And then we have to evaluate x at B, and then we have y and z remain free times ds. Okay. And then we also have to subtract from that, because this is the negative there. It's going to be P evaluated at A times yz ds. And it's again going to be over the same square, right? It's going to be over CD Cartesian product with EF. Okay. So clearly this looks like a fundamental theorem of calculus here. CD cross EF. So this looks like the partial derivative with respect to x. And then we're going to evaluate it at A. We're going to integrate it from A to B dx. And that's all inside ds, the original integral that we had here and here. Okay? So this, of course, can become, we've iterated this integral, but we can de-iterate it by just indicating that that's the integral over the entire volume of the partial of P with respect to x dv. All right, so you can assume then we could do the same thing for the top and bottom of our box and the front and back of the box as well. So together then, and note then that we'd add all of those together. So if we said now so what we'd get there is if we got the y flux, that would be equal to the volume over E, which is this entire box. That would be, and then the z flux would also be the volume integral over the partial of r with respect to z dv. You add all those together, and I'll just put out a new sheet of paper here. So total flux is equal to the double integral over the entire surface of f dotted with n ds is going to be equal to the volume integral over E of the partial of P with respect to x plus the partial of Q with respect to y plus the partial of R with respect to z dv. And of course, that is precisely the divergence of the vector field. So that constitutes a little proof here of this idea. So let's now compute a straightforward example. We can do that. I'm going to just do number 9 in the book. Okay, so let's start with an example here, which is going to be, we want to integrate, find the total flux of f, and I'll write down f. It's going to be the vector field x squared sine y x cosine y and minus xz sine y. Okay, over, we want to find the over, and we have to have the surface S defined by what is called the quote-unquote fat sphere. Which is defined as, it'll be x to the 8th power plus y to the 8th power plus z to the 8th power equals 8. So this shape, it sort of looks like a kind of like a sphere. You think of it as a sphere because it's the sum of the x, y, and z components to some even power equal to some sort of radius, but to the 8th power rather than the 2nd power. So it's difficult to understand what the shape of the sphere is, but it's certainly some sort of round sort of object. But it won't be completely round. It'll just be rounded. But I don't know exactly what that looks like. We could plot it for sure, but let's, instead of trying to compute what that surface is, appeal to the divergence theorem to see if computing the divergence of our vector field helps us understand something about the total flux. So again, what we can do is compute the divergence, and that's going to be the partial of p with respect to x. In that case, it'll be 2x sine y. Okay, and we're going to add that to the partial of q here. That's p, and this q, and that's r with respect to y. And then we get a minus x sine y. And then we also get we have to add again here the partial of this component r with respect to z, and that becomes again a minus x sine y. All right, notice that there's 2 x sine y's there, and then a minus 2 of them there. So the net divergence is 0. So recall that when we have a divergence equal to 0, it implies that we have incompressible F. So if F is the velocity field of some fluid, that means that for every components coming into some point, there's also the same as leaving. So the net balance of our of what's coming, going, and going through any small little region is going to be 0. So we're not going to. So we have some. So there's no compression going on of the fluid if it were a fluid. So that means then the total flux, which we didn't know how to compute the surface, that's going to be equal to over the volume of whatever that volume is of this object. But we know that the divergence was 0 dV. So that means the integral of 0 over any region is going to be 0. So the total flux is 0. So we see that by using the divergence, we could take what would otherwise be a very complicated surface to integrate over. It turns out by looking at the divergence, we found a much simpler, we got very quickly to the solution that we wanted in this particular example. So that's another idea. So let's talk again now. Let's revisit this idea of what it means. Why does divergence of the vector field why does it represent the net out or inflow of F at a point? And it's pretty simple. We can use the divergence theorem again. So again, say that E is a small cube, with, I'll call it volume E, is small. Okay? So we want to compute the divergence of V over this small cube, dV, and we know that's equal to the flux through cube. Okay, so that's equal to the surface integral dotted with the surface normal ds. Okay, so now if E is small enough, and recall that we need that F has continuous derivatives. So when we mean F has continuous derivatives, that means that over the region of E, which is really small, the derivatives of F won't change very much. That's what continuity really means when you break it down. It means that over small regions, you expect small changes in the derivatives of F. And that means as long as E is small enough, that means then that the divergence of F will be it'll be constant over E, right? Because if it's not constant enough, we can just make E smaller, and such that the divergence we can effectively say is constant, and that implies then that flux is going to be equal to, and again, if this is a constant inside this volume, that means we can bring it outside. Of course, that's the volume of our box. Okay. So again, we have this little box centered at some point. We want to know the inflow and outflow of our vector field through that box. And we're going to make it small enough, make this box small enough so that we can bring the divergence outside, because it's basically constant over this small box. So what we're saying then is, then we can take this whole thing and divide it by the volume of the box. And that implies then that the flux per unit volume, so that's the flux through the box, is equal to the divergence. Okay, so that's the flux per unit volume, and this should be equal to the divergence. So that's exactly the expression we wanted the divergence to have. Okay, so that's nice. So one last point here, in order to let you guys go, is how to connect. So how to connect Stokes with divergence. So recall that the Stokes theorem, we can always write it like this. We have some curve C. We have some surface that we put attaching to our curve. And we have some outward normal, call it N. And we know what we're really talking about is the flux of the curl of F is equal to dotted with the normal, ds, is equal to the work. over the work over C. So, of course, this surface, it's not closed. In fact, there's a hole that is kept open by this path integral around here. So we see that that this surface over this region is only partial. We don't have this closure here, right? So recall also, one of the properties of the curl was that the curl of any vector field, if we want to call that G, that if we take the divergence of any curl field is always 0, right? So now let's say that if I want to fill in this hole that we have here, I'll just put a plane. I just put another surface that connects to create this. I'm going to call that surface S tilde, right? So if I have the surface integral of S union with S tilde over our curl of F ds, but we know that this is a divergence-free. We need to put dotted with the normal there, ds. There we go. I can break that up into two pieces. As such, call that S tilde again, curl F dot N ds. Okay, so we know that this is divergence free. Right? So that means that, and this of course is a closed surface here, so we know that that's equal to the volume integral over the enclosed region inside of enclosed by the surface S and S tilde. And of course this was equal to 0, so that's equal to 0. All right, so both of these then are equal to 0, right? So now what we have here though, right, was this integral right here. Again, I'm going to write it down there. That was equal to the work. Through Stokes' theorem, that was equal to the work going around C. All right. So, I think I wrote. I wrote my arrows going the wrong direction. So I'm gonna put them that way. There we go. Better. Of our force field, dr. Okay. So that was that. So here's the work, and here is the flux through what we can call the region S tilde. Okay, so it's the flux of our curl vector through there. All right, so we can rewrite that. Because they're both equal to 0, we can say that the work now is equal to the negative of S tilde curl F dot N ds. All right, so that's another connection that we can write. So what's going on here? And this looks a lot like what we call Faraday's law. So Faraday's law in physics is part of electromagnetism, states that if we have F, and that's going to be in our electric field, and then we have our another vector field, which we'll call B, which is the magnetic field. Okay, so these two fields are related through what we call Faraday's law, which is stated as such that the partial of B over time. So now our electric fields and our magnetic fields could be functions of time. Is equal to the negative curl of F. Okay. So from before we had written down that so if we have some loop, which we're going to write like that, but actually we're gonna go around it that way, like before, and that's our loop of and we'll think of that as a loop of wire. Okay, and we stated that the work, and now we're going to think this is actually going to be an electric potential. Is equal to pushing our charge. We're going to push some charge around this loop according to the electric field, dr. So that represents a voltage. Okay, and that's going to be equal to negative of the surface S tilde that covers this region here of the curl of F ds dot n ds. Okay, so now what we can do is replace the curl of F with this physical principle determined by Faraday, which is that the voltage now over that loop is going to be equal to the surface integral. So we're going to replace the curl, the negative curl here, with this. The derivative of our B, our magnetic field, over time, dotted with n, ds. So it's the flux of the derivative of time over that region. And what we can do then is pull, because we're assuming all of our partial and our vector fields are smooth and they're continuous, and all of the derivatives are continuous, we can pull that outside. So this represents the rate of change of the magnetic flux through loop of wire is equal to the voltage around the wire. So now you see how we can take Faraday's law, which is written, and this is one of the Maxwell equations, and by using Stokes' theorem and using the divergence theorem together, we were able to imply that we were able to generate something that was more useful, which is how to generate, if I have a time-changing magnetic field going through this loop of wire, we can actually generate a voltage. And of course, this is the principle by which electric motors and electric generators can create voltage by moving magnets, which is or by moving magnets, which is what generates an electric field. If we move magnets across a loop of wire, and that of course creates a time derivative change in our magnetic flux through this field, we can generate voltage, which then powers most of our world, and it keeps the lights on and keeps the computers on. So that's one really great application of Stokes and divergence theorem together put into one, which is Faraday's law. All right, thanks very much.